Throughout his life, Einstein published hundreds of books and articles. He published more than 300 scientific papers and 150 non-scientific ones. On 5 December 2014, universities and archives announced the release of Einstein's papers, comprising more than 30,000 unique documents. Einstein's intellectual achievements and originality have made the word Einstein synonymous with genius. In addition to the work he did by himself, he also collaborated with other scientists on additional projects including the Bose-Einstein statistics, the Einstein Refrigerator and others. The Annus Mirabilis papers are 4 articles pertaining to the photoelectric effect, which gave rise to quantum theory, Brownian motion, the special theory of relativity, and E=mc2 that Einstein published in the Annalen der Physik Scientific Journal in 1905. These 4 works contributed substantially to the foundation of modern physics and changed views on space, time, and matter. The 4 papers are: Einstein's first paper submitted in 1900 to Annalen der Physik was on capillary attraction. It was published in 1901 with the title Folgerungen aus den Kapillaritätserscheinungen, which translates as Conclusions from the Capillarity Phenomena. 2 papers he published in 1902–1903, Thermodynamics, attempted to interpret atomic phenomena from a statistical point of view. These papers were the foundation for the 1905 paper on Brownian motion, which showed that Brownian movement can be construed as firm evidence that molecules exist. His research in 1903 and 1904 was mainly concerned with the effect of finite atomic size on diffusion phenomena. Einstein returned to the problem of thermodynamic fluctuations, giving a treatment of the density variations in a fluid at its critical point. Ordinarily, the density fluctuations are controlled by the second derivative of the free energy with respect to the density. At the critical point, this derivative is zero, leading to large fluctuations. The effect of density fluctuations is that light of all wavelengths is scattered, making the fluid look milky white. Einstein relates this to Rayleigh scattering, which is what happens when the fluctuation size is much smaller than the wavelength, and which explains why the sky is blue. Einstein quantitatively derived critical opalescence from a treatment of density fluctuations, and demonstrated how both the effect and Rayleigh scattering originate from the atomistic constitution of matter. Einstein's Zur Elektrodynamik Bewegter Körper on the electrodynamics of moving bodies was received on 30 June 1905 and published 26 September of that same year. It reconciled conflicts between Maxwell's equations, the laws of electricity and magnetism, and the laws of Newtonian mechanics by introducing changes to the laws of mechanics. Observationally, the effects of these changes are most apparent at high speeds, where objects are moving at speeds close to the speed of light. The theory developed in this paper later became known as Einstein's special theory of relativity. This paper predicted that, when measured in the frame of a relatively moving observer, a clock carried by a moving body would appear to slow down, and the body itself would contract in its direction of motion. This paper also argued that the idea of a luminiferous ether, one of the leading theoretical entities in physics at the time, was superfluous. In his paper on mass-energy equivalence, Einstein produced E=mc2 as a consequence of his special relativity equations. Einstein's 1905 work on relativity remained controversial for many years, but was accepted by leading physicists, starting with Max Planck. Einstein originally framed special relativity in terms of kinematics, the study of moving bodies. In 1908, Hermann Minkowski reinterpreted special relativity in geometric terms as a theory of spacetime. Einstein adopted Minkowski's formalism in his 1915 general theory of relativity. General relativity (GR) is a theory of gravitation that was developed by Einstein between 1907 and 1915. According to general relativity, the observed gravitational attraction between masses results from the warping of space and time by those masses. General relativity has developed into an essential tool in modern astrophysics. It provides the foundation for the current understanding of black holes, regions of space where gravitational attraction is so strong that not even light can escape. As Einstein later said, the reason for the development of general relativity was that the preference of inertial motions within special relativity was unsatisfactory, while a theory which from the outset prefers no state of motion, even accelerated ones, should appear more satisfactory. Consequently, in 1907 he published an article on acceleration under special relativity. In that article titled On the Relativity Principle and the Conclusions Drawn from It, he argued that free fall is really inertial motion, and that for a free-falling observer the rules of special relativity must apply. This argument is called the equivalence principle. In the same article, Einstein also predicted the phenomena of gravitational time dilation, gravitational redshift and deflection of light. In 1911, Einstein published another article on the influence of gravitation on the propagation of light, expanding on the 1907 article, in which he estimated the amount of deflection of light by massive bodies. Thus, the theoretical prediction of general relativity could for the first time be tested experimentally. In 1916, Einstein predicted gravitational waves, ripples in the curvature of space-time which propagate as waves, traveling outward from the source, transporting energy as gravitational radiation. The existence of gravitational waves is possible under general relativity due to its Lorentz invariance, which brings the concept of a finite speed of propagation of the physical interactions of gravity with it. By contrast, gravitational waves cannot exist in the Newtonian theory of gravitation, which postulates that the physical interactions of gravity propagate at infinite speed. The first, indirect, detection of gravitational waves came in the 1970s through observation of a pair of closely orbiting neutron stars, PSR B1913+16. The explanation of the decay in their orbital period was that they were emitting gravitational waves. Einstein's prediction was confirmed on the 11th of February 2016, when researchers at LIGO published the first observation of gravitational waves, detected on Earth on the 14th of September 2015, exactly 100 years after the prediction. While developing general relativity, Einstein became confused about the gauge invariance in the theory. He formulated an argument that led him to conclude that a general relativistic field theory is impossible. He gave up looking for fully generally covariant tensor equations, and searched for equations that would be invariant under general linear transformations only. In June 1913, the Entwerf draft theory was the result of these investigations. As its name suggests, it was a sketch of a theory, less elegant and more difficult than general relativity, with the equations of motion supplemented by additional gauge-fixing conditions. After more than 2 years of intensive work, Einstein realized that the whole argument was mistaken and abandoned the theory in November 1915. In 1917, Einstein applied the general theory of relativity to the structure of the universe as a whole. He discovered that the general field equations predicted a universe that was dynamic, either contracting or expanding. As observational evidence for a dynamic universe was not known at the time, Einstein introduced a new term, the cosmological constant, to the field equations, in order to allow the theory to predict a static universe. The modified field equations predicted a static universe of closed curvature, in accordance with Einstein's understanding of Mach's principle in these years. This model became known as the Einstein world or Einstein's static universe. Following the discovery of the recession of the nebulae by Edwin Hubble in 1929, Einstein abandoned his static model of the universe, and proposed two dynamic models of the cosmos, the Friedmann–Einstein universe of 1931 and the Einstein–de Sitter universe of 1932. In each of these models, Einstein discarded the cosmological constant, claiming that it was, in any case, theoretically unsatisfactory. In many Einstein biographies, it is claimed that Einstein referred to the cosmological constant in later years as his biggest blunder. The astrophysicist Mario Livio has recently cast doubt on this claim, suggesting that it may be exaggerated. In late 2013, a team led by the Irish physicist Cormac O'Rafeartai discovered evidence that, shortly after learning of Hubble's observations of the recession of the nebulae, Einstein considered a steady-state model of the universe. In a hitherto overlooked manuscript, apparently written in early 1931, Einstein explored a model of the expanding universe in which the density of matter remains constant due to a continuous creation of matter, a process he associated with the cosmological constant. As he stated in the paper, in what follows, I would like to draw attention to a solution to equation 1 that can account for Hubble's facts, and in which the density is constant over time. If one considers a physically bounded volume, particles of matter will be continually leaving it. For the density to remain constant, new particles of matter must be continually formed in the volume from space. It thus appears that Einstein considered a steady-state model of the expanding universe many years before Hoyle, Bondi and Gold. However, Einstein's steady-state model contained a fundamental flaw and he quickly abandoned the idea. General relativity includes a dynamical spacetime, so it is difficult to see how to identify the conserved energy and momentum. Noether's theorem allows these quantities to be determined from a Lagrangian with translation invariance, but general covariance makes translation invariance into something of a gauge symmetry. The energy and momentum derived within general relativity by Noether's prescriptions do not make a real tensor for this reason. Einstein argued that this is true for a fundamental reason: the gravitational field could be made to vanish by a choice of coordinates. He maintained that the non-covariant energy-momentum pseudotensor was in fact the best description of the energy-momentum distribution in a gravitational field. This approach has been echoed by Lev Landau and Yevgeny Lifshitz, and others, and has become standard. The use of non-covariant objects like pseudotensors was heavily criticized in 1917 by Erwin Schrödinger and others. In 1935, Einstein collaborated with Nathan Rosen to produce a model of a wormhole, often called Einstein-Rosen bridges. His motivation was to model elementary particles with charge as a solution of gravitational field equations, in line with the program outlined in the paper. Do gravitational fields play an important role in the constitution of the elementary particles? These solutions cut and pasted Schwarzschild black holes to make a bridge between two patches. If one end of a wormhole was positively charged, the other end would be negatively charged. These properties led Einstein to believe that pairs of particles and antiparticles could be described in this way. In order to incorporate spinning point particles into general relativity, the affine connection needed to be generalized to include an antisymmetric part, called the torsion. This modification was made by Einstein and Cartan in the 1920s. The theory of general relativity has a fundamental law, the Einstein field equations, which describe how space curves. The geodesic equation, which describes how particles move, may be derived from the Einstein field equations. Since the equations of general relativity are nonlinear, a lump of energy made out of pure gravitational fields, like a black hole, would move on a trajectory which is determined by the Einstein field equations themselves, not by a new law. So Einstein proposed that the path of a singular solution, like a black hole, would be determined to be a geodesic from general relativity itself. This was established by Einstein, Infeld, and Hoffmann for point-like objects without angular momentum, and by Roy Kerr for spinning objects. In a 1905 paper, Einstein postulated that light itself consists of localized particles, quanta. Einstein's light quanta were nearly universally rejected by all physicists, including Max Planck and Niels Bohr. This idea only became universally accepted in 1919, with Robert Millikan's detailed experiments on the photoelectric effect, and with the measurement of Compton scattering. Einstein concluded that each wave of frequency f is associated with a collection of photons with energy hf each, where h is Planck's constant. He does not say much more, because he is not sure how the particles are related to the wave. But he does suggest that this idea would explain certain experimental results, notably the photoelectric effect. In 1907, Einstein proposed a model of matter where each atom in a lattice structure is an independent harmonic oscillator. In the Einstein model, each atom oscillates independently, a series of equally spaced quantized states for each oscillator. Einstein was aware that getting the frequency of the actual oscillations would be difficult, but he nevertheless proposed this theory because it was a particularly clear demonstration that quantum mechanics could solve the specific heat problem in classical mechanics. Peter Debye refined this model. Throughout the 1910s, quantum mechanics expanded in scope to cover many different systems. After Ernest Rutherford discovered the nucleus and proposed that electrons orbit like planets, Niels Bohr was able to show that the same quantum mechanical postulates introduced by Planck and developed by Einstein would explain the discrete motion of electrons in atoms, and the periodic table of the elements. Einstein contributed to these developments by linking them with the 1898 arguments Wilhelm Wien had made. Wien had shown that the hypothesis of adiabatic invariance of a thermal equilibrium state allows all the blackbody curves at different temperature to be derived from one another by a simple shifting process. Einstein noted in 1911 that the same adiabatic principle shows that the quantity which is quantized in any mechanical motion must be an adiabatic invariant. Arnold Sommerfeld identified this adiabatic invariant as the action variable of classical mechanics. In 1924, Einstein received a description of a statistical model from Indian physicist Satyendra Nath Bose, based on a counting method that assumed that light could be understood as a gas of indistinguishable particles. Einstein noted that Bose's statistics applied to some atoms as well as to the proposed light particles, and submitted his translation of Bose's paper to the Zeitschrift für Physik. Einstein also published his own articles describing the model and its implications, among them the Bose–Einstein condensate phenomenon that some particulates should appear at very low temperatures. It was not until 1995 that the first such condensate was produced experimentally by Eric Alan Cornell and Carl Wieman using ultra-cooling equipment built at the NIST Gila laboratory at the University of Colorado at Boulder. Bose–Einstein statistics are now used to describe the behaviors of any assembly of bosons. Einstein's sketches for this project may be seen in the Einstein Archive in the library of the Leiden University. Although the Patent Office promoted Einstein to Technical Examiner Second Class in 1906, he had not given up on academia. In 1908, he became a Privatdozent at the University of Bern. In Über die Entwicklung unserer Anschauungen über das Wesen und die Konstitution der Strahlung, The Development of Our Views on the Composition and Essence of Radiation, on the Quantization of Light, and in an earlier 1909 paper, Einstein showed that Max Planck's energy quanta must have well-defined momenta and act in some respects as independent, point-like particles. This paper introduced the photon concept, although the name photon was introduced later by Gilbert N. Lewis in 1926 and inspired the notion of wave-particle duality in quantum mechanics. Einstein saw this wave-particle duality in radiation as concrete evidence for his conviction that physics needed a new, unified foundation. In a series of works completed from 1911 to 1913, Planck reformulated his 1900 quantum theory and introduced the idea of zero-point energy in his second quantum theory. Soon, this idea attracted the attention of Einstein and his assistant Otto Stern. Assuming the energy of rotating diatomic molecules contains zero-point energy, they then compared the theoretical specific heat of hydrogen gas with the experimental data. The numbers matched nicely. However, after publishing the findings, they promptly withdrew their support, because they no longer had confidence in the correctness of the idea of zero-point energy. In 1917, at the height of his work on relativity, Einstein published an article in Physikalische Zeitschrift that proposed the possibility of stimulated emission, the physical process that makes possible the maser and the laser. This article showed that the statistics of absorption and emission of light would only be consistent with Planck's distribution law if the emission of light into a mode with n photons would be enhanced statistically compared to the emission of light into an empty mode. This paper was enormously influential in the later development of quantum mechanics, because it was the first paper to show that the statistics of atomic transitions had simple laws. Einstein discovered Louis de Broglie's work and supported his ideas, which were received skeptically at first. In another major paper from this era, Einstein gave a wave equation for de Broglie waves, which Einstein suggested was the Hamilton-Jacobi equation of mechanics. This paper would inspire Schrödinger's work of 1926. Einstein was displeased with modern quantum mechanics as it had evolved after 1925. Contrary to popular belief, his doubts were not due to a conviction that God is not playing at dice. Indeed, it was Einstein himself, in his 1917 paper that proposed the possibility of stimulated emission, who first proposed the fundamental role of chance in explaining quantum processes. Rather, he objected to what quantum mechanics implies about the nature of reality. Einstein believed that a physical reality exists independent of our ability to observe it. In contrast, Bohr and his followers maintained that all we can know are the results of measurements and observations, and that it makes no sense to speculate about an ultimate reality that exists beyond our perceptions. The Bohr–Einstein debates were a series of public disputes about quantum mechanics between Einstein and Niels Bohr, who were two of its founders. Their debates are remembered because of their importance to the philosophy of science. Their debates would influence later interpretations of quantum mechanics. In 1935, Einstein returned quantum mechanics, in particular to the question of its completeness, in the EPR paper. In a thought experiment, he considered two particles which had interacted such that their properties were strongly correlated. No matter how far the two particles were separated, a precise position measurement on one particle would result in equally precise knowledge of the position of the other particle. Likewise, a precise momentum measurement of one particle would result in equally precise knowledge of the momentum of the other particle, without needing to disturb the other particle in any way. Given Einstein's concept of local realism, there were two possibilities: 1, either the other particle had these properties already determined, or 2, the process of measuring the first particle instantaneously affected the reality of the position and momentum of the second particle. Einstein rejected this second possibility, popularly called spooky action at a distance. Einstein's belief in local realism led him to assert that, while the correctness of quantum mechanics was not in question, it must be incomplete. But as a physical principle, local realism was shown to be incorrect when the aspect experiment of 1982 confirmed Bell's theorem, which J. S. Bell had delineated in 1964. The results of these and subsequent experiments demonstrate that quantum physics cannot be represented by any version of the picture of physics in which particles are regarded as unconnected independent classical-like entities, each one being unable to communicate with the other after they have separated. Although Einstein was wrong about local realism, his clear prediction of the unusual properties of its opposite, entangled quantum states, has resulted in the EPR paper becoming among the top 10 papers published in Physical Review. It is considered a centerpiece of the development of quantum information theory. Following his research on general relativity, Einstein entered into a series of attempts to generalize his geometric theory of gravitation to include electromagnetism as another aspect of a single entity. In 1950, he described his unified field theory in a Scientific American article titled On the Generalized Theory of Gravitation. Although he continued to be lauded for his work, Einstein became increasingly isolated in his research, and his efforts were ultimately unsuccessful. In his pursuit of a unification of the fundamental forces, Einstein ignored some mainstream developments in physics, most notably the strong and weak nuclear forces, which were not well understood until many years after his death. Mainstream physics, in turn, largely ignored Einstein's approaches to unification. Einstein's dream of unifying other laws of physics with gravity motivates modern quests for a theory of everything, and in particular string theory, where geometrical fields emerge in a unified quantum mechanical setting. Einstein conducted other investigations that were unsuccessful and abandoned. These pertain to force, superconductivity, and other research. In addition to longtime collaborators Leopold Infeld, Nathan Rosen, Peter Bergman and others, Einstein also had some one-shot collaborations with various scientists. Einstein and de Haas demonstrated that magnetization is due to the motion of electrons, nowadays known to be the spin. In order to show this, they reversed the magnetization in an iron bar suspended on a torsion pendulum. They confirmed that this leads the bar to rotate, because the electron's angular momentum changes as the magnetization changes. This experiment needed to be sensitive, because the angular momentum associated with electrons is small, but it definitively established that electron motion of some kind is responsible for magnetization. Einstein suggested to Erwin Schrödinger that he might be able to reproduce the statistics of a Bose-Einstein gas by considering a box. Then to each possible quantum motion of a particle in a box associate an independent harmonic oscillator. Quantizing these oscillators, each level will have an integer occupation number, which will be the number of particles in it. This formulation is a form of second quantization, but it predates modern quantum mechanics. Erwin Schrödinger applied this to derive the thermodynamic properties of a semi-classical ideal gas. Schrödinger urged Einstein to add his name as co-author, although Einstein declined the invitation. In 1926, Einstein and his former student Leo Szilard co-invented and in 1930, patented the Einstein Refrigerator. This absorption refrigerator was then revolutionary for having no moving parts and using only heat as an input. On the 11th of November 1930, U.S. patent 1,781,541 was awarded to Einstein and Leo Szilard for the refrigerator. Their invention was not immediately put into commercial production, and the most promising of their patents were acquired by the Swedish company Electrolux.